Okay, we're in business. Today, this is a pun. The topic is GOTO building a state machine. And another way of saying it is that we could say we are building a state machine using GOTO in fourth. So the task, we want to accept the input from a CSV formatted file. Last month, I did a talk about this using a different method. So this time we are expanding it and bringing it a little more, making it a little bit more general and contemporary. So we're going to take a CSV formatted data, generally in my case written by Excel. We're going to parse that file and regenerate the original data structures because in the original form, of course, there are lots of embedded little control things you don't see. And the CSV file is just pure text only. So we've got to go isolate the data elements from that pure text stream. And along the way, as you would in any fourth program, do some diagnostic information. And then as a separate project someday, classify the input into data types, because I'm trying to translate from Excel files into a matrix system. So the choices, well, one possibility would be a classic parsing. You can just set up some loops, scanning over the text using begin again, and then logic if then else to separate out the elements. I did a quick look at that, and it got pretty bulky and a little bit messy. And so then I thought, how about a state machine? Well, one classic is table driven, where every state machine element is one line on a table, and then you use the entries in the table to select inputs, outputs, decisions, and so on. And then the coding and parsing got to be a big deal on that. So then I wrote using case statements and what turned out to be recursive structure. And I'd never really done any production recursion before, and I just kind of automatically fell into the fact recursion worked beautifully in this situation. However, it's not general, and as you parse your way through text, you are building a huge chain of recursive calls. So I thought, let's try the classic state machine, which uses a GOTO. Each element just calls subsequent elements. But then you say there's no GOTO in fourth. Well, that's true. So let's create one. And so inadvertently, I just kind of fell into the fact that I had to write a GOTO where one code word calls it, one word calls another and never returns. So a quick definition on a finite state machine. It consists of a number of software nodes, and for sake of generality, I'll call them a number of nodes. Each node is individually activated by one other M node. And the inference on this is that a node can be called by any of M nodes, it means it can call itself. It can accept sensor inputs, it can initiate actions, and then it can pass control to one of the M nodes, as I said, including itself. So here's a code example. We're going to jump right into the code, and then we'll come back a little bit and we'll generalize why we're doing what we're doing. Here is the core element that makes this all work. We're going to use this routine, fourth word, to examine the first character in a data element. And since this is a GOTO, we do not want to return to the calling. This will be called by a state machine. This is one of the state machine elements. It has been called by a state machine, but we don't want to return to that element. So therefore, we go to R from drop. We'll go in the return stack and drop the calling address. So now this code sequence is on its own. It's an orphan. It has no place to return to. It can only execute ahead. Now we'll do in character and in character. This fetches the next character from the input stream, brings it to the stack, and it increments the pointer to the next character. So now we drop into a case statement, because from this first character, we need to extract information. If it turns out it is a hex OD, that is your carriage return. And so in this case, it will print out a field of whatever it's gathered so far, and it will jump to the next character, and the exit returns. Now we'll talk about this return process later, but this is the exit from the chain of state machine elements. Up to this point, you can imagine that several state machine elements have called one another. You hit the end of line, you will get a display, and then increment to the next character, and then return to the outermost calling routine. We'll see how that is done in a moment. So that's our master exit. If, on the other hand, we encounter a comma, that's a separator between fields. So in this case, now we will print out the field we've got, and we'll recurse, which means we're going to go back to the first character of the next element. So this is our continuity element to element. If we get a quote, we'll see later on that that's a reserved character, a special character. And so we'll call the state machine element that processes a delimited field. This will go to enter a delimited field. And notice the arrows on the right-hand side with a GOTO beside it. What it points out is these are points of the program that will never be returned to. Even though we're calling a fourth word, the execution will never return back to this point. If none of these cases have taken place, we have the character on the stack that we have extracted, and so we'll record that character. We'll add it to the output stream with record character. And then now we will drop into a non-delimited field, because at this point, we know we're processing ordinary text. So we drop into that non-delimited field. And again, this is a GOTO. We will never come back here. Finally, you hit end case, and the note is there that execution will never reach this point, because somewhere along the way, it has exited this state machine element node and go into the next. Here's our driving program, run CSV. First is we load the files, and this goes into some text buffers. And then we set the input character to 0 and the output character to 0, some housekeeping. And now we enter the state machine. So at the begin point, we hit SM link. And this is a transition into the state machine world. And we will talk about this again in just a moment. This is the point at which, when the state machines hit an end of line, they will return to this point. And then the my file size tells us how many characters we have in the input file, and the in character tells us how far we've processed. If there's any rows remaining, we'll execute the while portion. This sets the output character back to 0 and repeats back up at the begin, and the SM link starts a new line. So this is what chews our way through the file line by line by line. At the end of each line is an hex OD. And so we will execute until the hex OD. Finally, when we're out of characters, after repeat, we'll execute. You'll do a carriage return, and you'll get the message state machine closed. So how do we get in and out? There has to be an intermediate link here, which I call SM link, state machine link. So this is called by that outer program, and it actually enters the first state machine node, which is the first character SM. It enters that. Now remember, there is no return. It will not return to this point, because when it calls that first character SM, that routine immediately throws away the return point. So it does not return here. Even though this is the entry, it doesn't return here. What it does is it returns back one level before, and it will return just following that SM link word. So this is the essence of how the GOTO works. The GOTO uses that intermediate start to begin the node chain. Upon returning, it will come to the execution just after the SM link word. So now back to the, we've seen getting into and getting out of the state machine. So the CSV format, comma separated values, uses a comma to separate each data element. If you have text between double quotes, this is a literal string used as is because you have to be able to accommodate a comma. If in your data stream you see a comma, that indicates end of a data element, but how can you accommodate a real comma? So you put that field in quotes, which means we have a literal string that will be output just as is. However, what if you have a double quote within a literal string? Well, there's another exception then. So to represent a double quote within a literal string, you have two double quotes. So now we've been able to accommodate using our delimiting characters, which are commas and quotes, but with these two exceptions, they can be decoded and handled. And finally, the end of line is demarked by an ASCII CR and LF, and the end of file is end of file with nothing, no CR, no LF. The end of file means you terminate with nothing. So here are a couple of cases we have to handle. The first is if we have a comma in our field, if the box in the center shows the output, XXX, comma, XXX. The input shows a quote that's leading and trailing to mark that literal field. If you have a quote in a literal field, the quote here would be XXX, double quote, XXX. Then again, you have double quotes in the middle to denote that. And then here is a kind of a combination where you have, if you have leading double quotes, then you end up having three quotes in a row. So your book ended by three quotes in a row, leading and ending, and that will then bring out a complete quoted phrase. So here's my test data. The first row is A, B, C, D, E, F as plain text, then with a comma embedded, then with leading and trailing quotes, and then finally leading and trailing quotes with a comma in the middle, then a single quote, and then really an extreme case, which is a quote, comma, and a quote. The second row is the same information repeated again, just so we know we can handle more than one row at a time. This is what it looks like in the raw form. So this is what's on the file. And you can see that's a mishmash of commas and quotes in there. And especially at the very lower bottom right side. Look at all those quotes and commas. Double quotes, commas, commas, commas. And we have to decode that. So there are these state machine nodes. The first one we already seen, which is the one that decodes the first character. After the first character, then if we have a non-delimited field, that is just pure text that has no reserved characters in it, ordinary text, then one node decodes that, which is called next characters. On the other hand, if it is a delimited field, delimited by quotes, then we have another one of next characters in a delimited field. And finally, we need to process at the very end when we have a trailing delimiter, because we're at the end of one of the data fields, we end up with a concluding quote, and you'll see we have to handle that specially. So here is the diagram. We'll start at the driver, the top left corner. This is that loop program that runs the decode CSV. Remember, it calls the intermediate link program, which is essentially a stepping stone into the state machine nodes. And so the first character one we've seen does a decoding looking for either a legitimate character or a double quote or a return. If it has no double quote at the beginning, the first character branches down to the bottom right to a non-delimited field. And the non-delimited field then can call itself repeatedly, and we don't show the exits because remember the exits are would exit upon a comma or a return. So for an ordinary character, it calls itself. For a comma, it goes to the, on the left-hand side, you can see the little comma in the circle. That returns us to a first character. If it executes a return, a CR, that returns us back to the driver. If, on the other hand, the first character is a double quote, then it goes to a separate node, which decodes the delimited field, and it has the same process. If it's an ordinary character, it calls itself, and it absorbs those characters into an output buffer. Upon reaching a double quote, it goes into a little routine that handles the ending delimiter. And the end delimiter is now looking for the comma, the CR, or another double quote. And so remember, in all these cases, whenever the ending characters are encountered, the comma and the CR, they return as appropriate. So remember, there's a lot of go-tos on here. This is the most non-structured code in the world, where every node is under a set of rules that leads to the next node. And then finally, upon that final CR, it uses the return stack to return 2 levels up back to the original driving program. So we'll do a quick review of that processing the first character. Again, remember the from our drop removes the return path. We get the input character. We run through the case statements, and we'll either get an exit on a OD, we'll get a recursion to a new field with a comma, and a double quote will give us a delimited field. The recursion on a comma means it's really an empty field. If our very first character is a comma, it means this field is empty, so it will be reported as such. Lacking all of that, we have a non-delimited field, ordinary characters, which is recorded. We then go to a non-delimited field, and that works in this fashion. Again, the non-delimited field is a state machine node, so it will drop its return calling address. It will get an input character. In this case, it's a little bit simpler. It's either looking for an OD, hex OD, which is an exit, meaning the end of line, or it gets a comma, which means end of field. And in that case, it loops back and processes the first character again. Lacking any of those exits, it just records the character. And because we're now in a non-literal field, it will recurse. It will execute the non-delimited field again, working its way through the data fields until it gets an exit. The delimited field is simpler, or is similar. Again, it drops the return address, gets a character. And in this case, it should not encounter an OD. If it encounters an OD, this is an error abort because it's a format error in the input text. If at this point it gets an ASCII quote, it may or may not be at the end of a delimited field. It may be part of a double quote, a double quote, or it may be the ending of the field. So we have a special routine that handles the ending delimiter. And lacking that, we are in the middle of a literal field, so it will record that character and recurse calling itself. The ending is, you might say, it's kind of a cleanup. It's how do we handle the end of the delimited literal field. Again, we drop the return address, and now the situations we encounter are similar as before, but with some small differences. The OD, it means we are at a legitimate end of a field, so we will print that field. We'll increment to the next character, which steps over the LF that follows, and we'll exit back to the outer calling routine to get the next line. If we encounter an ASCII comma, now we are in a literal field, and the ASCII comma, I take it back. We've reached the end. The second double quote has reached the end of the field, so we can accept a comma at this point as end of field. The field be presented, and now we loop all the way back to the first character SM, which is continuing along that line of text until we get an OD. If in this case it encounters an ASCII quote, now we've gotten 3 ASCII quotes in a row. And so while you take ASCII quote, puts a ASCII value on the stack, record character records that. Now in the output stream, we have inserted the quote, which is responding to the existence really of a double quote. And now we loop back to that delimited field again. And if none of those cases execute, we have an error in this case, a format error, because one of those 3 cases has to have happened. So here's our wrap up, our resulting report. We see in our original, this was the original Excel file that I had right back at the start. We can see we have the 2 lines, which are essentially duplicates of one another for testing. And this is the output we get. Now our print format in this case, for testing purposes, we want to identify the data fields in a clear way. So I just put a stick character vertical bar at the beginning and end of each of the outputs. So this helps us in our debug. And along the way, I would have 2 or 3 of these working, and I could follow how far along the conversion went, and then make whatever changes necessary to complete it all. And at the end, we know it's all good, because remember that outer calling routine at the end ends up with the sequence state machine closed. So here's what we saw and did and learned over the last couple of journeys into state machines. There are a number of different architectures. The one that I explored was recursion, which I programmed, table-driven, which I didn't. There are other methods, which if you go to Wikipedia, they have very exhaustive treatments on those. And in my last work on this, I used the recursion, but I saw some limits because its control flow is a little difficult, and you are stacking a lot of stuff on the return stack as you parse through your files. Also, because of the recursion testing, it's a little bit more difficult. I believe the system I'm using can't properly trace through recursion. So instead, I went to the classic design, in which case I claimed I invented, although maybe other people have done it likewise. And I invented a method for developing a GOTO in Forth, and this was developed out of sheer animal necessity. So do we have any questions or comments?
Similar problem. This is way back in the 90s, and so I don't remember exactly the code, but I was writing a terminal program to parse the characters coming in, and I had factored my code well, and then I found out if I had an error, I had to jump all the way back up, and I did your R from drop to get back up.
Yeah.
It worked good. It was a good.
You use what you got to use.
Yeah.
Yeah. If you need it, you need it.
Sometimes you need a GOTO.
Yeah. And I'm jokingly calling it a come from. Instead of a GOTO, it's a come from, because you you know where you've come from.
Yes, and today I don't think there are any ports where R from drop doesn't exit out of the calling routine. But in the day, back in the days, there were some ports that I ran into that R from drop didn't work.
Yeah, Win32 Forth actually has a word that's a code word that is R from drop all together, mushed together, and that way they do this at the machine level rather than interpreting level. Because I can see the problem doing it interpreting level, where you crash yourself when you pull R from, you may crash the system.
Exactly.
One
And
thing, one thing I'm very impressed with what Ron Aaron did is he's got tail optimization in most words. I'm not sure exactly how what conditions it can't be used, but essentially instead of having returns, which is it simply will replace the return with a GOTO. And so it some point or another it has to hit a return, but essentially if the last function in the in the definition is part of another definition. I mean, anyway, this tail recursion elimination, and undoubtedly it's the sort of thing that Brad probably has a lot of expertise in. But it essentially is GOTO. I mean, what's the difference between a jump and a GOTO?
well, it still has the problem that it assumes that what is on the top of the return stack is an executable function. And that has not always been true in every forth.
Good point.
Yeah.
Yeah.
It's we have. I don't know many of those forths that have survived anymore because of this problem. They always have a conversion problem that they can't do an R from drop. But yeah, there were a few.
You know what the reasoning was why they used the return stack for data? I've used it for data within a colon definition, like as a local variable, but I've never put data on it because you would never pass to another definition with data on the return stack. Doesn't make any sense, does it?
It does in certain cases. Now I don't remember all the details.
Well, if you were to do this inside if you were doing the R from drop inside a do loop, there you've got control parameters on the return stack. So you wouldn't use an R from drop inside a do loop.
Yes, that is one.
Although if you're patching code, or doing something weird, you could do some R from drops to get rid of control parameters to exit a do loop prematurely.
Yes.
Begin until.
Actually, my implementation of stack frames, which is from some fourth thing. I mean, it's not my structure, but all it does to create a stack is put a pointer to the previous stack, and so it's but it is a piece of data that's been left on the return stack. Oh no, it isn't. It's on the. Forget that. Putting stuff. Well, yeah, like Don said, within a definition. I mean, return the damned return stack clean.
Well,
begin until.
And we have gravitated to that being the pretty much only solution that works in all cases. And so those other forths have disappeared.
How about begin until? Do they use a return stack typically?
No, it's a branch.
So you could do a loop.
The until reaches a embedded return address in the object code.
Yeah, because until would be looking at the data stack, right? So
until looks at the encoded stream of executables for an address back to a begin.
Saying is, could you do a begin? For example, you create a variable, a counter variable. You do a begin, and then you do R from drop, and then, test that variable, maybe it's just a memory variable with until, and then when it goes 3 times, it exits the loop. Would that break with most fourths?
To get
I don't
rid
remember
of
how I
do
did it.
loop, to get rid of just the do loop, probably not, but it still is broken on a for loop.
Okay, the question is begin until.
Yes, begin until puts an address. Or I thought you were
inline address on the object code.
right. I thought you were dealing with a do loop that you jump over the other things. The stuff that was left on the stack from the do loop.
Well, the do loop uses control parameters on the return stack, but
Right.
until does not.
Correct.
So you
Until
could do a
uses
loop.
parameter on the data stack.
Yeah, so you could use begin until to do a multiple R from drop. That's probably what I did.
Right. Right. Now, I think what ended up breaking all of them is at some point in time, we standardized a begin while, repeat. If you're following me, you can have multiple whiles.
Yeah, I think the other thing that happened is a little more memory became more commonplace, and people
Right.
start making extra stacks for other stuff.
Yep.
So if you did another data stack or a stack for flags, true, false, or a stack for
Yep.
floating point, or a stack for, oh, sorry, I didn't mean to mention that. That's the work of the devil. I can prove floating point is the work of the devil. In the olden days, we used to have these separate math coprocessors. If you ever put your finger on them, they were really hot.
Yes, they were hot.
Floating point, the work. All right. On that cheerful note, I'd like to move on. It's time for the group photo. Brad, are we ready to light the fuse on that?
Sure. Could everybody get on camera if you want to be in the photo?
If you don't want to be in the photo, turn off your camera or log off and log back on in 2 minutes. So if you're on the lam, now's the time to bail. All right.
I see a few more folks popping up, so I'll give it 1 second more.
Mr. Hare, you were at the lunch. We've got a group photo we'd like to publish. Is that okay with you?
Yes, that would be fine. Thank you.
Okay, I'm gonna take the photo. Ready, and got it.
So Dave will be publishing that on our website. So you'll be exposed to the world for your lack of good judgment in terms of what Zoom meetings you attend.
Yeah, Brad, you need to add some audio feedback when it takes the camera picture.
Yeah. Well, I'm just screenshotting, so you know.
Yeah, I know. We need to.
To be honest, I'm not sure with the screenshot whether it freezes at the moment I hit the keystroke or at the moment I select the region, but because I'm not grabbing the whole screen, I'm grabbing a region, and then anyways. Well,
hard to tell. I've not figured that out myself. Yeah, I don't know.
So Edward Borowski, are you ready to go?
I think so. Can you hear me?
We can hear you just fine.
Okay, let me figure out how this screen sharing thing works. I've actually got 3 computers today, all hopefully networked. So let me figure out how this screen sharing works. I think I want the browser. Yes. And let me copy this address into the chat. And then go to, that's not it. I got to download it. Okay, can you see that?
Excellent. Very good.